All right, so welcome back to the fluid mechanics section of the Civil FE exam review. In this video, we're going to be going through fluid statics. And so I have a few practice problems for you all. So let's go ahead and dive in. All right, so number one says, calculate the pressure at a depth of 10 meters in a fluid with a density of 1,000 kilograms per meter cubed. Neglect atmospheric pressure. All right, so what is the information that we're given? We are given the depth, which is 10 meters. We're also given the density. That's the symbol P. But the density is 1,000 kilogram per meter cubed. All right. And it says neglect atmospheric pressure, or AP. All right. So what are we trying to find? The pressure at the point in the fluid. At the point with depth of 10 meters, right? All right. So, let's say you have, what does this visually look like, right? So, now I've been using blue a little bit, but really, so you have water or a fluid in this cup, and I will, let's erase that. Hope that you like my drawings, by the way. So let's say our fluid is in a cup, right? This is our cup. The top, right? And we are trying to find the pressure at this point. Here is the distance from here to here is 10 meters, right? And we just want to find the pressure with that depth of 10 meters. And we know the density of this fluid is 1,000 kilograms per meter cubed. All right. So now let's look at how we get this. So I don't know I don't know the formula that I need for a pressure, but what I can do is I will get in the fluid mechanics section of this and see if I can start looking at pressures. Specifically of a submerged. Okay, so here it's like forces on a, okay, so the pressure on a point at a vertical distance h is what we have. Below the surface is P is equal to, what does P stand for? P is pressure. P atmospheric, or PATM is atmospheric pressure, which we're neglecting. The rho is a density. That's the symbol for density. G is gravity. And then H is the distance, that vertical distance. Okay, so let's solve, all right? We have, I believe, everything that we need. So P is equal to PATM plus rho GH. All right. So we're neglecting atmospheric pressure, so that just goes away. And we are left with P is equal to, what is my rho? Well, 1,000 kilograms per meter cubed. Rho is just the density, times the gravity, which gravity in a fluid is, gravity in general is 9.81 meters per second squared. And then what's our height? Our height is 10, our depth, which is h, 10 meters. All right. Now, once we get our units, we get, or once we cancel our units, we get 98100 kilograms over meters per second squared. Okay, or A. Let's look at number 2. Number 2 says calculate the buoyant force acting on a wooden block with the volume of 0.02 meters cubed immersed in water. Assume the density of water is 1,000 kilogram per meter cubed. All right. What are we given? We're given the volume, which is 0.02 meters cubed. We're given the density, which equals 1,000 kilogram, 1,000 kilogram per meter cubed. Okay. Anything else? No. What are we trying to find? Buoyant force. All right. What is a buoyant force? All right. What is buoyant force? So let's take a look, because I don't know. So just gonna search boy, and I spelled buoyancy wrong. It's B-U-O. All right. So here it says buoyancy. The buoyancy force exerted on a submerged or floating body is equal to the weight of the fluid displaced by the body. So it's equal to the weight. So that's the information that we need for this. So let's draw this out, because I think that'll help us a little bit. So say we have water again, right? And we got our cup. Cup of water. All right, but now we have this wooden block. Right. And we have, we want to show the forces on this. So we have a, whatever that this is, pulling down. And we got gravity. And we probably got the mass. And then we have the force buoyancy. It's pulling up on this thing to keep it afloat. So we just want to find what that is. So if we look at this, how do we get the weight of this wooden block, right? Well, if you didn't know, density is equal to mass divided by volume. Okay. We are given, we have our density right here. We have our volume here. So our mass is equal to density times the volume, which is equal to 1,000 kilogram per meter cubed times 0.02 meters cubed, which is going to give us 20 kilograms. Okay. Now that we have our mass, all right, the weight of this object, the weight of the block is equal to mass times gravity. All right. So what is the mass? 20 kg times 9.8 meters per second squared. And that gives us what? Should get 196.2 kilograms meters per second squared. And now we just need our units to be in newtons. So 1 Newton is equal to what? Well, we can search this. So in our handbook, we can go to our unit conversions section. And from what I'm seeing, 1 Newton is equal to 1 kg times m over s squared. So 1 Newton equals 1 kg m over s squared, which means that we have 196.2 kilogram meters per second squared. And if we do a unit conversion, 1 kg m over s squared is equal to 1 Newton. So these units cancel and we just are left with 196.2 newtons, which closest answer would be C. All right. Let's look at number 3. All right, this one says, determine the force exerted by water on a vertical rectangular plate submerged in a fluid with dimensions 3 meters by 2 meters. The gate extends 5 meters below the fluid surface. Okay. So what information are we given? Well, we do know the dimensions. 3 by 2 meters. Depth equal to 5 meters below the surface. All right, we're trying to find the force exerted by water. All right, so we're trying to find the force exerted by water. All right, so when it comes to this type of stuff, right, force, and we have, do we have pressures? Like what information do we have that we can use? So first thing, if we're trying to find force, then let's go to the section where this may be helpful. So let's go to the fluid mechanics section. I'm just clicking through my bookmarks. Okay. And so when I'm going through, see force here and area, right? So the force exerted, I know that we're using water. And we have P, right? We have pressure. So the pressure of water. Or we can get we know the density of water. We don't know the pressure of the water at this point of 5 meters, but I believe that we can solve for it. So let's start with T, or the stress, is equal to sum of the forces over this, or the change in force of the change in area. So formula number 1 needed would be stress is equal to, we don't have a change in force and we don't have a change in area, so it's going to be F over A. Okay. All right. So if we draw another picture for this, right, we have this not really a cup though, but we'll say it's contained in a rectangular shape, and then you have this gate that is 5 meters below the surface. And so we want to know, I'll just say, this is the rectangular gate. And the water, so if we look at this in a different form, basically the water is pressing down on this rectangular grate, right? And so we're just trying to find that force that's being exerted on there. So if you look at, kind of think about this in 3D, you got it 3 meters by 2 meters. And so the area that we would be using would be 3 times 2, right? So area is equal to 3 meters times 2 meters equals 6 meters squared. All right, so A we have. All right, what about the stress? Well, in this case, the stress is going to be a normal stress, right? Acting on it. It's not going to be I'm not going to be using a tangential stress, right? The normal stress is 90 happening 90 degrees on this rectangular gate. And so what we're going to do is we're going to, from our formulas, we see that the tangential stress, or T sub n, is equal to negative P. Well, what's P? P is pressure. All right. And what is how do we get pressure? Pressure is going to be, should just be rho GH. Most of the time we're negating atmospheric but in this case, yeah, the difference in pressures, if there's some different fluids, it's just going to be negative rho GH, difference in pressures. Okay, so negative P, which equals to negative density times G times H. Okay, do we know what rho is? Well, rho equal to it, our fluid is water, so rho is going to be the density of water, which in this case is here 1,000 kilograms per meter cubed. All right, so we have P. What about G? G is gravity, just 9.81 meters per second squared. And what is H? H is our depth below the surface, which equals 5 meters. All right, so we have all the things that we need. And now it's just a matter of plugging and chugging to get our P, our negative P. So N is equal to negative P, which is equal to negative 1,000 kilograms per meter cubed times 9.81 meters per second squared times 5 meters. And so I get 49,000 kilogram all over meters second squared. All right, and then we have T sub n. So what are we trying to find again? Trying to find force. So we now have T n, we have A, and so now we can find what we're looking for, which is F, right? So T is equal to F over A. And to get F, we multiply A times T, which equals 6 meters squared. All right, we already got that. Times 49,000 kilograms meter second squared, which after that you're gonna get a huge number, but it's ultimately gonna give you 294 kilonewtons. And so our answer is D. So a lot of trying to figure out what's what. So it's kind of like they didn't give us a lot of information, but they gave us just enough to be able to get to the next step. So first, we took what we had. We found a formula that we could use to solve for force. We're given that we had a fluid of water, so automatically you have the properties of water, which a part of those properties is your density. And from there, we could find pressure given the depth. And then we had a rectangular grate. So it's like we just kept working, kept chugging. But ultimately, the important thing is that you know what you're solving for, which is force in this case. So hopefully this made sense. This concludes this section of the fluid mechanics practice. The next section is going to be energy, impulse, and momentum of fluids, and that'll be our last section for fluid mechanics.